Yesterday we graphed basic rational functions that looked similar to the one on the screen right now. Here's the rational parent function, f of x equals 1 over x. We have two branches to this rational function. And today we're going to start graphing more advanced rational functions. So you'll see ones graphed like this today, where you have two vertical asymptotes instead of just one in the parent function. And ones like this, where again you'll have two vertical asymptotes as opposed to the parent function that only has one. Now it's important when we see these different pieces of the more advanced rational functions that we know when we're going to graph them, we have to test 1 point in the first, 3 points in the second, and 1 point in the third. This will allow us to figure out whether or not we're in the negative section for our branch, both sections, or in the positive section for the branch. So we're going to be doing a lot of testing points to graph advanced rational functions. So here's the first one from your notes. F of x equals 3x over x plus 1 times x minus 2. My first step after recognizing that this is rational, because I have the division sign, is finding the vertical asymptotes. So from yesterday we found the vertical asymptotes for what value of x does y not exist by setting our denominator equal to 0. So I'm going to do that first. I'll then use ZPP and get my first vertical asymptote as x equals -1, which would be the vertical line through the x-axis at -1, and x equals 2. 1, 2. Vertical line through the x-axis at 2. This just split my graph into the 3 sections. I know I'm going to have different branches in each part of the graph. For my horizontal asymptote, that one doesn't change at all until tomorrow. So y equals 0. Now, as I said earlier, we're going to have to test a lot of points. So let's create a table. You might need scratch paper for this. The first point I have to test is something in this first interval of my domain, which let's write the domain. I have 3 pieces to my domain. My first interval is -infinity to -1, that first asymptote. Open parentheses because we don't include the asymptote of -1. My second interval is from -1 to 2. And I'm going to test 3 points in that interval. And then my last interval is 2 to infinity. We'll check the range after we graph it. So in my first interval from -infinity to -1, I'm going to test -2. You could test -3, -4, -5, any of these to see whether that branch is opening down in the negatives or up in the positives. So to test -2, I'm going to plug that into the original rational equation for x. So I'll show my work up here. I have 3 times x, which is -2. Continue inputting -2 in for x. And then simplify to find your output. 3 times -2 is -6. -2 plus 1 is -1. And that value is being multiplied by this value, -2 minus 2, which is -4. Be careful with your negatives because that's going to affect whether your graph is opening up or down, and that's what we're trying to find here. So I have -6 divided by +4. Which simplifies to -3/2. Sometimes it's easy to see it -3/2 also as -1.5. Might be easier for us to graph -1.5. Either is fine. So I'm going to graph this point, -2, -3/2, which is -1.5, and I know now that my branch is in the negatives, so I can sketch the rest of my branch. Now, if you wanted to be more accurate, you could test other points, like -1.5, which we'll see tomorrow, -2.5, -3, -4, and so on, to have a more accurate branch. But because we tested this and what we know about rational parent function, we know that this being a negative value at -2 will create the whole branch in the negative, so we'll just sketch it. The middle branch, from -1 to 2, I have to test 3 points. The reason I have to test 3 points in the middle is because I might be opening up and then down in the positives and negatives, right? Kind of like the cubic function, or I might look like the quadratic function in that middle branch. Just depends on the rational. So I do have to test a point in the middle, kind of where the vertex would be of your interval, and then a point to the left and to the right of that. So for our particular function, it's kind of hard because we don't have 3 tick marks for the middle to exist at. So my middle that I'm going to choose is going to be at 0. Inputting 0 into this rational, I'm going to have 0 in the numerator, and 0 divided by any number is still 0. You could write out the algebra and simplify to still get 0 if you wanted to. So we got 0, 0 is one of my ordered pairs. Now I have to test a point to the left and to the right. Well, to the left, I think the easiest input value between 0 and -1 is -1/2. Now, don't freak out. Inputting fractions is no big deal. We can do it. I'm going to use the scratch paper to input this -1/2 into the original rational function. So I have 3 times -1/2 divided by inputting -1/2 for x Now when I simplify this, I want to think about how to add and subtract fractions. I'm okay with multiplying. To multiply fractions, you make 3 over 1, and then multiply straight across in the numerator and the denominator. So we have -3/2. Be careful when you're adding and subtracting fractions, though. We have to have common denominators. So -1/2 plus 1, I'm going to rewrite as -1/2 plus 2/2. I converted 1 to 2/2, so they had common denominators. I'm going to convert the 2 in the other factor to 4/2. Because 2 is equivalent to 4/2. This will allow me then to simplify further. So we have -3/2 still in the numerator. -1/2 plus 2/2, +1/2. -1/2 minus 4/2, -5/2. I'm going to multiply straight across. So remember, in the denominator, those two factors are multiplied by one another. So I have -3/2 over, or divided by, -5/4. Now this still doesn't look like an ordered pair that I can graph. So I'm going to continue simplifying. When you divide by a fraction, when you divide by -5/4, that's the same as multiplying by its reciprocal. The reciprocal of -5/4 would be -4/5. Now I can multiply straight across, and I get a value that's way more easy to plot on my graph. So I have 12 in the numerator, 10 in the denominator, which simplifies to 6/5. 6/5 is positive, so -1/2 and positive 6/5, which is about 1 1/5. Right about there. Now I have to test and see what's happening on the other side. Still in this same interval of -1 to 2. I might go back up, like a quadratic shape. I might curve back down. So I have to test a value here to see where my rational function is tending towards. I'm going to test x equals 1. I'm going to continue to use my scratch paper. No fractions here needed, so I'll have a little less algebra. 3 times 1. In my numerator, I'm inputting 1 over 1 plus 1 times 1 minus 2. That simplifies to 3 over 2 times -1, which simplifies to -3/2, or -1.5. I'll plot that point, 1, -1.5, and now I can see that I have the cubic shape in the branch. Lastly, I have to test a point in the third interval of my domain, from 2 to infinity. I'm going to test 3. Use my last piece of scratch paper here to test 3. Again, I'm inputting into the original function, 3 times 3 over 3 plus 1 times 3 minus 2, which simplifies to 9 over 4 times 1, so 9/4. 9/4 on the graph I know will be in the positive y values, but I'm converting this to a mixed number of 2 and 1/4 to help me graph a little easier. I'll then sketch the branch, and there's my rational. The range from lowest y value to highest y value, because of that middle branch, is -infinity to infinity. And I can see my x and y intercepts are both at 0. That's how you graph a more advanced rational function.